Hi everyone, note 6.3 are on evaluating logarithms. So if you take a look at question number 1, it says that Jackson knows that a rumor spreads very quickly. He tells 3 people a rumor. By the end of the next hour, each of these people has told 3 more people. Each person who hears the rumor tells 3 more people in the next hour. Jackson has written an algebraic model where n of t is equal to 3 to the power of t plus 1 to represent the number of people who hear the rumor within a particular hour, where n of t is the number of people told during the hour t, and t equals 1 corresponds to the hour during which the first 3 people heard the rumor and started telling others. So in which hour will an additional 2,187 people hear the rumor? So right here, I have my equation n of t is equal to 3 to the power of t plus 1, and we know that our n is 2,187. So that's 3 to the power of t plus 1. So what I'm going to try to do right now is I'm going to try to find what number is 2,187 if I were to have a base of 3. So let's go ahead and figure this out right here. So if I do 3 to the power of 4, I know that's 81. So let's try 3 to the power of 6. We know that's 729. Multiply that by 3, we get 2,187. So that means 3 to the power of 7 is 2,187. So we're going to say 3 to the power of 7 is equal to 3 to the power of t plus 1. Eventually, we're going to use logarithms to solve this, but for right now, if you notice right here, we have the same base, and we've got our exponents right here, so we can set our exponents equal to each other. So we can simply just say 7 is equal to t plus 1. So here, when I isolate t, I can say t equals 6. So I can say, therefore, at hour 6, an additional 2,187 people hear the rumor. Okay. We're going to revisit this question later on this unit to see how we can use logarithms in order to solve this question here. Okay? So let's just write the definition of what a logarithm is one more time, just to be 100% sure everyone's okay with this. So log base b of x equals y is just simply saying right here that x to the power of y, b to the power of y is equal to x, where b right here is going to be our base and y is going to be our exponent. Okay, so right here, I'm going to set this equal to x right here. And so what this is going to say is 4 to the power of x is equal to 64. Well, I know that 64 is equal to 4 to the power of 3, and I know that because if I were to multiply 4 by itself 3 times, I get 64. So therefore, I can say x equals 3. Okay? For the next one right here, I'm going to say, I'm going to set this equal to x, so I'm going to say 2 to the power of x is equal to negative 4. So I want to know what value of x for my exponent can I raise 2 to a power of and get a negative answer. And that's impossible because I know that 2 to the power of x looks like this, and negative 4 is way down here, so they'll never intersect with each other. 2 to the power of any number is always going to be a positive number. We'll get really small numbers for negative exponents right here, but it will never go below 0. So this right here means that there is no solution to this question right here. All right. The next one that we have right here, I'm going to say equals x again. And so this is going to say 3 to the power of x is equal to 1 over 27. Well, I know 27 is equal to 3 to the power of 3, so that means that 1 over 27 is 3 to the power of negative 3, because we always do the reciprocal whenever we have a negative exponent. So we know that 3 to the power of x is equal to 3 to the power of negative 3, which means that x has to equal negative 3. Okay? And then in our last one that we have here, we've got log base 5 of the cube root of 25. So I'm going to set this one equal to x right here as well. And I'm going to say 5 to the power of x is equal to the cube root of 25. Well, I know that 25 I can rewrite with a base of 5 to the power of 2. And I'm going to choose 5 because I want my bases to be the same. Now, if I want to take the cube root of 25, that means that that is the cube root of 5 squared. And when I take a cube root of something, it means I'm raising it to the power of 1/3. And if you remember, if you have a power to a power, you always multiply your exponents. So this is 5 to the power of 2/3. So here I get 5 to the power of x is equal to 5 to the power of 2/3, making x equal to 2/3. Okay? And that's how we're going to evaluate our logarithms. All right, so question number 3 says to determine the approximate value of log base 5 of 47. So log base 5 of 47, I'm going to set equal to x. So I'm going to say 5 to the power of x is equal to 47. Now I need to know 47 is 5 to the power of what? So I don't know exactly what it's going to be. So right here I'm just going to do a bunch of guessing and checking until I can get to my answer. We're going to revisit this question in a couple of videos because we're going to learn some properties that are going to help us solve these equations right here. But for now, we're just going to go ahead with guess and check. So I know 5 to the power of 2 is going to be 25, and 5 to the power of 3 is 125. So I know that my answer right here has to be somewhere between 2 and 3. So I'm going to try 5 to the power of 2.4 and 2.5. Let's try 2.5 and see what happens right here. So 5 to the power of 2.5, I end up getting 55.9, so that's too high. So I'll try 5 to the power of 2.3. And I get 40.5, so that's too low. So I'll try 5 to the power of 2.4. And I get 47.59, which is close to what I want, but a little bit too high. So I'll try 5 to the power of 2.39, and I get 46.8, which is pretty close right here. So what I'm going to do is I'm going to say it's approximately 2.39, okay? So again, let's try this, 5 to the power of 2.39. Right here, I end up getting this answer right here. So I can say 5 to the power of x is approximately equal to 5 to the power of 2.39. So x is equal to, approximately equal to 2.39. Okay, and I think next video is the video where we're going to be able to revisit this question and actually be able to get closer to a correct answer for this. Okay? Okay, so question number 4 says to evaluate each of the following logarithms, and these here are going to help us identify some important properties that we need to know. So I'm going to set this equal to y. So this means 6 to the power of y is equal to 1. And I know that if I have 1, it's anything to the power of 0. So to have the same base right here, I end up getting 6 to the power of 0. So y equals 0. Okay, now I just want to go to Desmos and try this out right here and see what happens if I were to type this in. So I'm going to go to functions miscellaneous, and I'm going to have log with my base here. And I'm going to put 6 right here. And then here I'm going to put the number, sorry about that, I'm going to put the number 1, and I get 0. But I want to know if this is true for just the base of 6, or if this is always true. So if I take a look right here, if I were to replace this 6 right here with, I don't know, 56, I still get 0. Okay? If I were to replace it with pi, I still get 0. If I were to replace it with 0.33333, I get 0. I don't know if it will let me replace it with x. Let's see. It will not let me replace it with x, but no matter what number we have as our base, it will always work for us. Okay? And if we take a look at this right here, like I could just say log base b of 1 equals y. So this is going to say b to the power of y equals 1. So I know b to the power of y is the same thing as b to the power of 0 because I need to have the same base. So y would equal 0. So we can say right here we have an important property that log base b of 1 is always going to be equal to the number 0. Always. Okay, that's a really important property that we need to write down. All right, our next one that we have here is log base 5 of 5 to the power of x, and I'm going to say this is y right here, okay? So I'm going to say 5 to the power of y is equal to this right here, which is 5 to the power of x. And since they have the same bases, I can conclude that y equals x. So I can just say that log base 5 of 5 to the power of x is just x because y is the same thing as x. So I can say here that this is just going to be x no matter what right here. Okay, and we can show that this is true using any base. So we can say log base b of b to the power of x. I'm going to set that equal to y. So this is saying b to the power of y is equal to b to the power of x. So therefore y equals x, which means that log base b of b to the power of x is simply just x. So that is another important property that we're going to write down, that log base b of b to the power of x is just simply x. Okay? All right, now for our last one right here, I'm going to set this equal to y. And this time I'm given my exponential relationship, and I want to switch over into my logarithmic relationship. So I know that my base here is going to be 6. So I can say log base 6 of my answer y is equal to my exponent, which is log base 6 of x. So therefore, since they both have the same logs with the same bases, I can conclude that just y equals x. So therefore, 6 to the power of log base 6 of x is simply x. Now, let's see if this is true for any base right here. So if I say any base to the power of log base b of x, I'm going to set this equal to y. So here I can say log base b of y is equal to log base b of x, which means that y equals x. So I can therefore conclude, my third conclusion right here is going to say that log base b, b to the power of log base b of x, and this should say b and not 6, is equal to simply x. So this is my third important property. So we have 3 important properties that we're going to be using in order to solve our logarithms. Okay? All right, that's it. Let me know if you have any questions, and I will see you later. Bye.